Good. So, hello everyone. So the plan for today is to finish conjugate direction methods, conjugate gradient, and then talk about Quasi-Newton methods. And if we have time, then we will come back a little bit to Newton methods to discuss its convergence rate with a bit more detail. If we don't have time, then you will do that during recitations. So let's recap quickly what we discussed last time. So we were discussing conjugate direction methods, right? And we discussed that it was originally developed for solving a quadratic problem. Like this, where this matrix Q was positive definite. And this problem was equivalent to solve this linear system Qx equals B, where Q is a positive definite matrix. And we proved that theorem that conjugate direction methods, if you already have the conjugate directions, then you can solve this problem at most n iterations. Just to remind you, the definition of conjugate direction was this, that k vectors seems I cannot use red. Okay, so k vectors d1, d2, dk, they are Q orthogonal or Q conjugate if their inner product, where the inner product is defined as di transpose q dj, is 0 for all different I and j's, right? And we discussed these two special cases. If Q is the zero matrix, then any two vectors are conjugate. And if Q is the identity matrix, then this is the traditional orthogonality definition. We proved this lemma that if Q is positive definite, then if we have k Q conjugate vectors, then they are linearly independent. The proof was very simple. And then we started to discuss why Q conjugacy is useful. And we come back to this quadratic problem, which has a minimum in x star. And because the vectors are linearly independent, we could just rewrite this x star in this form. And then we proved that the coefficient alpha I has this form, which has a very useful property, namely it doesn't contain x star. So if you know Q and B and you have the d naught, d1, dn minus 1 Q orthogonal vectors, then you can get these alpha coefficients just using, just calculating some inner products, right? And if we have the alpha I coefficients, then we have that x star has this form. And then we proved this conjugate direction theorem, which said that if we have n Q conjugate vectors, x naught is an arbitrary starting point. We update x's with these equations. That is the next x, xk plus 1 is the current x, xk plus alpha k dk. Where alpha has this update rule where in this equation gk is just the gradient at xk, then after n steps, indeed xn will be x star, the minimum of the quadratic function. Right? And the good thing about this is that we don't need to do any matrix inversion. If you have a linear system, generally you need to do matrix inversion, but with conjugate directions, you don't need to do that. So we proved this theorem. And then we discussed another theorem, which was the expanding subspace theorem, which had this form that if we have, again, n co-conjugate vectors, x naught is an arbitrary starting point. We update x's with this rule, and alpha k is the same as before. Then what actually happens is that at iteration k, xk is a minimum on this line, that is the previous point, xk minus 1, and you go to the direction dk minus 1, and you just need to find that alpha that minimizes this function. So you restrict your minimization to a one-dimensional minimization. And again, and also this xk is also a minimum of a k-dimensional minimization problem, where you are minimizing in this domain x naught, your starting point, and in that starting point you place this bk subspace, which was just the span of the first k conjugate directions. Right? And then we had this illustration that what happens is that you travel along these lines. You were in xk minus 2, then you went to xk minus 1, then you are in xk points. And this is in a span of x naught plus bk, where again bk is just all the previous co-conjugate directions. And in that xk point, you will minimize your quadratic function restricted to this subspace. And the proof was that we proved that the gradient vector gk will be orthogonal to this bk subspace. And we proved this by induction. And then we had this important corollary that gk is orthogonal to bk, that is, gk is orthogonal to all conjugate vectors whose index is less than k. And these bk subspaces, they are getting bigger and bigger. And at some point, at step n, it will be the whole space. And it proves that at xn, you find the minimum of your quadratic function. And this was the illustration what happens when you do conjugate directions. So first, you minimize in this subspace bk. Your minimum is xk. Then you minimize in a larger subspace bk plus 1. Your new minimum will be xk plus 1. And at some point, your B space will be the whole n-dimensional space, and then you are in X star. Any questions so far? So this is where we stopped last time. Questions? Everything is clear? So what we haven't discussed is how to find these conjugate directions, right? So we just said if we have these conjugate directions given, then what can we do? All that left is to discuss how can we generate these Q conjugate directions. Questions? Okay, so the plan for today is to discuss that, how to generate these conjugate directions. There will be some conjugate gradient methods where we use gradients, and using the gradients, we will generate these conjugate directions. And we will also discuss Quasi-Newton methods, which will do the same. And that's the plan for today. And in the next lectures, Ryan will talk about Karushkun-Tucker conditions and duality, and they will help us to generalize these methods to those problems where we have some constraints as well. So all these problems we discuss today is for unconstrained minimization. So we don't have any constraints on x's. We just say that x is in an n-dimensional space. But in practice, there are lots of problems where x is in a restricted space, and you still want to do some minimization there. Okay, and we will start discussing them next week. Okay, so here is the problem that questions? No? It's not on the website?
When you click it, it says forbidden.
Oh, permission. Yeah, after class, I will fix that. Unless, Ryan, can you? So I think when I uploaded the slides, I didn't give permission to anyone.
Okay, I'll try to fix that.
Yeah, other good questions? Yeah, I mean, it's very important, right? You might find yourself in difficulty if you cannot look at them. Okay, so given d naught, dn minus 1, q conjugate directions, we already have an update rule for alpha k. Right? The question is, how should we choose vectors d naught, dn minus 1 that are q conjugate? And we will use the conjugate gradient methods for this. So we will use the conjugate gradient method that actually uses the gradient to construct these conjugate directions. And an important property of this that previously we just assumed that you already have these d naught, d1, dn minus 1 conjugate directions. Here we won't assume that anymore. As we progress during the minimization, we will construct the next direction. Okay? So this is the pseudocode of the algorithm. So let x naught be an arbitrary starting point. Oops. Let d naught be the negative gradient in that point. So what's the negative gradient? It's b minus q x naught. Why? Because our function, if you remember, it was this function, this, right? F of x is this, and its gradient is qx minus b. Its negative gradient is b minus qx. For alpha k, we will use the same rule that we had before. And for the new point, we will also use the same update rule that we had before. That is, from xk, we move to xk plus alpha k dk. For the gradient, we will have this notation that gk is the gradient. And now this is the new step here. That is, the new conjugate direction will be constructed as the negative gradient at xk plus 1 plus a linear plus dk, the previous direction, multiplied with the scalar beta, where beta looks like this. Okay, so what we need here is that we already constructed dk q conjugate vectors, and the new one is just a linear combination of dk and the gradient at xk plus 1, where xk plus 1 is updated with this update rule. And what left here is to prove that this new dk plus 1, it will be indeed q conjugate. Yes?
Should that be gk plus 1?
Instead of minus?
No, like g sub k plus 1. In like between the xk plus 1 and the dk plus 1? Or is that g sub k, like for sure?
So which, can you point it?
How do I, is it the
Yeah.
button? Okay, this one.
This is just the gradient.
Oh, okay.
Okay,
so
so
you don't calculate.
yeah, so this is if you have a quadratic function. Oops.
Okay, so you're calculating it using xk. You're
Exactly,
not,
yeah.
Okay, and the
Oh,
other one
you do that for g, so it also means that gk plus 1 here, it will be q x k plus
okay.
1 minus b.
Thanks.
Other questions? Okay, so the good thing about this method that in contrast to Newton method, there's no need for matrix inversion. So what left here to do is that we need to prove that these new directions, how we constructed, they will be co-orthogonal. And this is formally stated in this conjugate gradient theorem, which just says this, that so the span of the first k plus 1 gradients is the span of these vectors. So you start from g naught, and you just multiply them with q. You can also prove that the span of these d vectors that we just constructed in the previous slide, it will be the same as the span of these vectors. And this property C, that's important to us, it states that these directions indeed co-conjugate. For alpha k, we use the same update rule that we had. And there's another important property here that you see that we generated bk with these update rules, which has q in it. But actually, you can prove that we could have generated bk with these update rules as well. Okay, so now the second important property here is that if we use this bk as an update rule, then in the pseudocode in the previous slide, let me go there. So this is the pseudocode. Then there will be no q here. There will be q only here in the gradient and in alphas, right? So q was the matrix of the quadratic system. We want to get rid of that because it's just difficult to store. So we saw that bk can be rewritten, that it won't contain q anymore. Gk is the gradient in that point. So if you have a system, so our goal is to generalize this whole system to other nonlinear functions. We discussed what's happening in quadratic functions. So gk is the gradient. If we have another function where we can calculate the gradient, then we don't need to calculate Hessian there, right? And for alpha, what we are going to do, that remember what was the definition of alpha? alpha was a point, so alpha k was that if you go to dk, what's the minimum into that direction? And if we replace that with a line search, then we will not need q there either. Okay, so in this way, we can have an algorithm that will not need the second derivatives, only the first derivatives. And uses the gradients and uses conjugate directions. Okay, so let's see in more detail how. So by the way, this pseudocode, any question about this? So we had this theorem here that we didn't prove, so that it would take some time, and we don't have time for that. So you might discuss this in recitation next week. But any question about this, what's happening here? Questions? Yeah.
Is this one similar to the Gram-Schmidt orthogonalization?
Exactly, yeah. So in Gram-Schmidt orthogonalization, you would do something very similar. The difference here is that the orthogonality definition. Yeah, right. Yes. Other questions? Okay, so let's see how to extend this algorithm to non-quadratic problems. So our problem again is to minimize a function f in the n-dimensional Euclidean space. And what can we do? We do quadratic approximation, right? So we calculate the gradient, and we calculate the second derivatives, the Hessian. But instead of Newton's method, we will use conjugate deduction methods using that pseudocode that we just discussed before. Right? So you start from a point x0. You do this pseudocode that we discussed in the last type for n steps. You generated n conjugate deductions. You move to a new point, and you restart the whole process. Why we restart the process after n steps? Yeah, because on this quadratic problem we converged, right? We are in a new point, and in that new point we do a new quadratic approximation. And also we don't have more conjugate deductions either, because there's just n in a n-dimensional space. Okay, so this is the algorithm in detail, that you start from a point x0, you compute a gradient, and you set the first direction to be the negative gradient. And xk plus 1 will be the minimum of this minimization if you go to direction dk and you use this quadratic approximation, and then you can calculate that the minimum would be this quantity, where instead of q that we had in previous slides, we just use this second derivatives. We calculate the gradient in xk plus 1, and if we still didn't converge in this quadratic problem, then we construct a new conjugate deduction using these update rules that we discussed. The only difference is that we replace q with the Hessian, and this is the derivative at xk. You do this for n steps, and after n steps, you restart the process and construct new gradients. Okay? So a nice property of this that you don't need to do line search because alpha k is set to this expression, but the bad property of this algorithm that you need to calculate the Hessian. So there's no free lunch here. Either you do line search. So here we don't do line search, but we need to calculate the Hessian in the algorithm. And again, a fix for this would be that for bk, we can use an update that I showed you in the previous slides that doesn't contain the Hessian. And for alpha k, you can just use a line search. And then, again, that wouldn't contain the Hessian here. OK? So that makes sense so far. So now we will discuss two important line search methods. And the first one is called Fletcher-Reeves method. And the pseudocode is exactly what we just discussed. You start from x naught, you compute the gradient. First direction is the negative gradient. Then you repeat this process for n steps. And now this is one difference, that xk plus 1 is alpha k dk, where alpha k is not a fixed number that you calculate with the Hessian, but you do a line search. And for bk, we use this form that doesn't contain the Hessian. Any question about the motivation or steps of this algorithm? So it's clear how it was motivated and how we got to this algorithm. Questions?
So in this formulation, you don't read step 3.
So steps, you do this for n steps, and then you go back again because so there are many different variants, but one variant is that you replace the whole step as you did before.
Okay.
Yeah.
For the previous method, you have to invert the Hessian matrix.
You don't need to invert. You just need.
It was in the denominator.
Yeah, but you multiply. This is the Hessian, and you multiply from left with the vector and from right with the vector. So you don't need to calculate the inverse, but you didn't need that, the Hessian. Yeah, that's a good point. Right. So in these methods, you don't need to calculate the inverse like you do that in Newton method, but you still need to calculate it.
Yeah.
And with the, if you do line search with conjugate gradients, then you don't even need to calculate the Hessian. But still, this might be a difficult step to do. Yes?
Previous update for beta k in the previous slide, should the numerator contain a Hessian?
Yeah, so there are two forms for that. This is so this is one form that contains the Hessian, but actually you can prove that there's an equivalent form where it doesn't contain the Hessian. Let me go to that slide. Let me find it. Yeah, here. So you can also use this as an update rule for the betas. So it just uses the norm, square norm of the gradient at k plus 1 and the square norm of the gradient at k.
But I think in that particular slide, the numerator is not a real number, so I think it needs to be Hessian in the middle.
Which one? Oh, this one?
Here. The numerator should contain a Hessian in the middle, right? Because it's no longer a real number in the numerator.
So here you talk about this one, and it's no longer. So it's.
Should the term in the middle be a Hessian there?
No, I think I just forgot to put a transpose there. Let me see. Yeah, you are right. So it should be this Hessian. Yeah, good point. And multiplied. Yeah, so this is the Hessian as well. Thanks.
In this, we're stopping step 2 after n iterations. Why do we stop after n? Because we're continuously reapproximating the quadratic, right?
Yeah, so it's just one variant, and there are other people who don't do that, indeed. I think the problem here is that after, if it's not a quadratic problem anymore, then it's kind of became a heuristic, and it's not known what's the best algorithm here, and people try different things, and indeed, there's one version where they restart the process, and in some other version, they don't do that. Other questions? Yep.
Previous slide, part A, are we using an xk plus 1 is equal to xk plus alpha k to 0?
Yes, xk plus. Good point. So other typos, I think we found like 10 already. No? Good. So this is one. So the Fletcher-Reeves method is one important conjugate gradient method. And there's another one, which is called Pollack-Ribéry. This Pollack is not that Polyak that Ryan mentioned in the backtracking. And here the only difference is we do the same as before, but this is the update for the betas. And again, there's no theory behind this, but experiments show that somehow this update works better than the previous one in applications. Okay? So now if we ask you to implement conjugate gradient method, you can do it if you fix those typos that we had in the slides, right? They want to use more moments but sometimes moment methods can work better, sometimes not, but that's all. There are some conditions when it's proven that it's better, but generally it's not known. Sometimes this algorithm works better, sometimes that one. And there are many different kinds of results on the rate as well of these estimators. So here is one. So as you remember, the Newton method has quadratic rate, right? So here, we cannot really get that, but we have something similar that is after n. So we will have this rate for the result, C is a constant. After n steps, the error will look like then it has a quadratic rate. And the intuition behind this is that after n steps, you basically solve like a Newton method because you approximate with the quadratic function and you solve what's the minimum there. And you can indeed prove this rigorously. But in the Newton step, we had that for the next step, we had this quadratic rate as well. Yep.
Do we have a support sign on the left side? Or it's like norm less than square?
It's norm. So the error is less than the squared on the square norm on the other. So it means that if the error is small, right, then this is much smaller than this. This is xk. This is k plus n. Yes.
N is the dimension, right?
Yes. So, yeah. N is the dimension. Mm-hmm.
Fletcher-Reeves method. So for the first for the step A,
the minimization problem for alpha, is it so in many cases?
No.
So
No, it's it's the same as with gradient descent, right? So you can try different approaches, but it's not always that easy, right? So you can do backtracking if you want. It's not that easy, but when it's easy, then it can be useful. Yeah, again, another heuristic that if you can calculate the Hessian, then you might not need this step. Okay, and here is just an example. We had a quadratic function, and this is what happens if you do gradient descent, starting from this x0 point. You jump and you would do the optimal step size. Then you would follow these points. But if you use conjugate gradient descent, then in 2 steps you would find the minimum. Right? We had quadratic functions. So this sound just means that it's time to have a break, and we will continue from here. So during the break, please don't just sit, but stand up, walk a bit, breathe. That might help. Okay, so let's continue. So as a summary, we discussed how to use conjugate direction methods to minimize quadratic problems without any constraints. And we also discussed how to use the gradient to generate conjugate gradients or conjugate directions that use gradients. And we discussed how to minimize non-quadratic functions using these methods. And we discussed a variant that used the Hessian. And we also discussed if we don't want to calculate the Hessian, but we are happy to use line search methods, then we can use conjugate gradient methods for that problem as well. And we discussed the Fletcher-Reeves and the Pollack-Ribeiro methods. Okay? And there are 3 announcements. One is there's a cell phone here, which seems to belong to no one. So if it's yours, take it. If it's not yours, then we should find whose this cell phone is. And you have an announcement too, right?
Yeah, okay, so the peer grading, there's a form in which you have to just submit the scores. So could you please do that soon? Yeah, that's it.
Okay, and the third one is that the slides should be available now. Of course, we finished, so it doesn't matter. No, but you can try the Quasi-Newton methods. Hopefully that should work. Oh, good. Okay, so here is the outline that we need to discuss. That we will talk about a modification of Newton's method, and its name, that's why it's called modified Newton method. And we will see that one big problem with Newton's method is that huge inverse there. And we will develop some update rules how to approximate the inverse. We will see the details later, but there will be one that uses rank 1 correction for the inverse. That method is called rank 1 correction. And there will be 2 methods that use an update rule where we change the Hessian with a rank 2 matrix in each step. And these two algorithms that we will discuss is the Davidson-Fletcher-Powell method and the Broyden-Fletcher-Goldfarb-Shano. So that is the DFP and BFGS methods for Quasi-Newton. I think they are the most famous algorithms for Quasi-Newton methods. But there are many other variants as well. Okay, if you want to read more about this topic, here are a couple of books that you can look at. So here is the motivation why we want to do this. So as we discussed, calculating the Hessian, it might be very difficult and costly. So the idea is that instead of calculating the Hessian, we want to approximate it. And we will see that Quasi-Newton methods, they are one way to do this approximation. And the algorithm will show that these Quasi-Newton methods will be somewhere between steepest descent and Newton's method. So in steepest descent method, you don't need to do any approximation of the Hessian. In Newton's method, you need the exact Hessian, and Quasi-Newton will be somewhere between these two methods. Okay, so again, our goal is to minimize a function over the whole n-dimensional Euclidean space. Just to remind you, if you are interested how to do the minimization when instead of the whole n-dimensional Euclidean space, you just want to do over a subspace, then next week we will come to that when we discuss interior point methods. So just to remind you, the gradient descent update rule was this. That is, the next xk is just the previous point minus a step size times the gradient. The Newton method update is the next point is the previous point minus the inverse of the Hessian multiplied by the gradient. Right? So the difference is that in gradient descent, we use alpha k. In Newton method, we use the inverse of the Hessian. And the modified Newton method is the combination of these two ideas. That is, xk plus 1 is xk minus step size multiplied by sk matrix and the gradient. And the question is, what should be those sk matrices that make sense? Right? So it's a special case. If sk is the identity matrix, then we got the gradient descent. If sk is the inverse of the Hessian, that's the Newton's method. So one important lemma here is that we can prove if sk is positive definite, then the direction in which we move, it's a descent direction. And the proof is exactly the same how we proved that for the Newton's method. That is, if it's a descent direction, it means that xk plus 1 minus xk, that vector, the inner product of that vector with the gradient should be negative. Right? That's the descent direction. I see some people frown here. So again, if you calculate the gradient of a function, the negative gradient points to the direction of the largest, where the function has descending the most, right? So the descent direction is that one. We say a direction is descent direction if the inner product with the gradient is negative. Okay, and the proof is very simple. So this is the gradient. What's xk plus 1 minus xk is minus alpha k sk, the gradient of f of xk. And now because sk is positive definite, alpha k is non-negative, so this expression will be negative. Okay, so let's discuss this update rule for quadratic problems first. So we have the same quadratic problem. This is f of x. And we want to minimize this, and we assume that q is positive definite. For the gradient, we will use the same notation, gk. So gk is the gradient at a point xk, and of course is qxk minus b. So this is the modified Newton's update rule. And now we have a lemma that which says that if alpha k is that alpha that minimizes this expression xk minus alpha skgk, then for alpha k we will have this expression here. Is the statement clear? Statement clear this side? Right, so we have this f quadratic function that we want to minimize in alpha, then for alpha we will have this expression as a minimum. Okay, the proof is very simple. So again, f is a quadratic function. This is xk plus 1. So what do we need to do? So here is this function f of x. That's a now it's a function of alpha actually, and we want to find the minimum of this in alpha. So what do we do? Yeah. So we calculate this, and it's very simple after that. So from this expression, we will have q times xk minus alpha skgk. That's here. And we need to calculate the derivative of this expression with respect to alpha as well. So that the transpose of this will move here. And if we calculate the derivative of this expression with respect to alpha, that will be b transposed skjk. And if we solve when it's 0, then after some calculation, we will have that indeed alpha k has this form. Okay? So here is a theorem about the convergence rate of this modified Newton method. So let x star be the unique minimum of point f, and let the error be defined with this slightly weird expression where so now the error is not just xk minus x star norm, but I defined a norm with this Q matrix. And so the error is this expression. This measures how far xk is from x star. And using this notation, you can prove that the error at point xk plus 1 is less than this expression multiplied by the error in the previous step. And here, bk and lowercase b and capital B is the smallest and largest eigenvalue of sk times q. Okay, so this is a convergence rate result. The question is when this convergence rate fast. Right, so when it's small, so the convergence rate is fast when this expression is small. When this expression is small, when beta k is the capital beta k is the lowercase beta k. So the largest eigenvalue is the smallest eigenvalue. And kind of shows that if this is the identity matrix, that's good for us. And so we want SKQ be the identity matrix. In other ways, SK in ideally is the inverse of the Hessian. Okay, we don't prove this, but you might discuss this during recitation. The proof is not that difficult. Okay, there's another modified Newton's method called classical modified Newton method, where instead of approximating the Hessian matrix, each k, you just do something very simple. You approximate it at x naught and use that in the rest of your life. And people really do that. And of course, now how good this approximation is, it depends on how the Hessian is changing during your process. Okay, so let's discuss more complicated algorithms, how to construct the inverse of the Hessian. So the idea will be that we want to construct the inverse of the Hessian using that knowledge that we have during the process, that we observe the function value and say we calculate the gradient as well. So there will be a couple of notation that's important for us. So you want to write it up or memorize quickly, because it might be a bit messy. So for the gradient, we use again this expression g. So gk plus 1 is the gradient at xk plus 1, gk is the gradient at xk. And we will have a new notation. Pk is how much we move from xk to xk plus 1. I will just keep using notation q for the Hessian, so it's the second derivative at xk. And we will need another notation, that's qk, which is how much the gradient change. So what's the difference between the gradient at xk plus 1 and xk? And we can say that under some smoothness conditions that this vector is close to the Hessian multiplied with xk plus 1 minus xk, that is pk, right? And in the quadratic case, it's not just an approximation, but it holds sharply. That is gk, the gradient at f is qxk minus b, and because of that, for qk, we will have that it's, by definition, gk plus 1 minus gk, and if I use that, I know what's the gradient now. It turns out that it's qpk. Okay. So this is what we know in the quadratic case, that for all k, we have this, and let h denote the inverse of the Hessian. And now the trick that we will use, that if we have n linearly independent directions, p naught, p1, pn minus 1, you remember the definition of these vectors. If we have n of them, they are independent, and we calculate the these vectors q as well. Again, you remember the definition, I hope. So q is defined by this, p is defined by this. Then we can calculate the Hessian in this quadratic case, right? Oops, so So think of this as a n by n matrix, and this is another n by n matrix. Okay? And because H is the inverse of the Q, for H we will have this expression as well. That will help us to estimate H. So if we have NQ and NP vectors, and they are independent, then I could estimate Q and I could estimate H as well. Yes, question? No? Okay, so our goal will be to construct an estimator of the inverse of the Hessian H, and that estimator will be denoted by HK. And we want this estimator, so this is an important property, we want this estimator, HK, to be consistent with this property here. That is at least up to time step k, HK plus 1, our estimator. If I multiply this with this matrix, I should get this matrix here. So that's important. So if you got lost here, you should scream. Okay, and of course, after n linearly independent steps, we would have that the estimation at time step n would be exactly the Hessian H. So there will be a couple of tricks that will help us to do this estimation. The first and simplest one is the so-called rank 1 correction. So again, we want an estimator that has this property. And what we do is that we will try to construct HK plus 1 in this form, that is HK plus a rank 1 correction. So AK here is a real number, and ZK is an n-dimensional vector. So we want to find a good AK and real number and ZK vectors with which this property will hold, assuming that this property holds for HK. But we want this to be hold for HK plus 1 as well. Okay? And here is a theorem. So if we assume that this holds, so this was our goal, and we update HK plus 1 using this rank 1 update, then from this it follows, then if there's a good update, then this update should be in this form, where you remember that PK was xk plus 1 minus xk, and qk was the difference between the gradients. Is that clear so far? What the theorem says, not the proof. So we want to find an update that has rank 1 correction. Why do we want that? That's the first question. Why do we do this way? The idea is because the Hessian is symmetric, so we want to update in that way that at least what we got, that will be symmetric as well. And if you have a symmetric matrix, you add a rank 1 matrix to that matrix, that will be symmetric. So we do that. We also want that consistency property on the top. And from these two, the consistency and the form of the update, it follows that HK has to be in this form. Okay, let's prove this. So this is what we know, that we have this consistency property and we have this update for H. Okay, from this, of course, it follows that pk is hk plus 1 times qk. We know what's hk plus 1, right? So if we substitute hk plus 1 here, then we will get this expression. And of course, this is just hk qk plus this term. Okay, if I remove from both sides hkq, then we have this expression. So now let's multiply this expression with its transpose and divide that by ak. Sorry. So I multiply this expression with its transpose and divide with ak. So I will have this expression here. And now what you can notice is that this is zk transpose qk, this is qk transpose zk, is just zk transpose qk squared. It's a real number. So we have this expression. Okay, so we got that hk plus 1 is hk plus ak zk zk transpose. But from this, right, we have that ak zk transpose is just this expression divided by this guy here. So for hk plus 1, we will have this form. And now we are almost done. The last thing we need to notice is that if we come back to this expression and we multiply this with qk transposed, then qk transpose pk is qk transposed hk qk plus qk transposed this expression here, and that's just ak times qk transpose ak squared. Okay, so from that, from this equation, we have that this expression is nothing else, just qk transpose pk minus this guy, and this is what we had to prove. So it's a little bit of calculations, but each step is very basic. So now we know if there's a rank 1 update for H with this consistency property, it has to be in this form. The next theorem, that this update indeed works. So we know that if we want an update that's consistent and uses rank 1 update, then HK has this form. And we need to prove that if we have this update, then at the end we will get this consistency property as well. So this is the theorem. So let Q be a positive definite matrix. Pi k plus 1 given vectors, and Qi is defined as earlier, that is Q times Pi. H naught is an initial symmetric matrix where we start the iteration from that. And now if we use this update that we just discussed, that's the only form the update can be, then we will have this consistency property that we wanted. So that's the theorem. And as a corollary, if P naught, Pn minus 1, they are independent, then at the n step, Hn will be the inverse of the Hessian. Okay? So using this, we can define the modified Newton method with rank 1 correction, which will be like this, that xk plus 1 is xk minus alpha k, hk, that's the estimation of the inverse of the Hessian, gk, that's the gradient at xk. For alpha k, we will use line search. So again, gk is the gradient. For h, we use that update that we discussed. P and Q, they were defined earlier. Pk is just xk plus 1 minus xk, and qk is the difference between the gradients. And that's the algorithm, and you do this iteration. So that's the Quasi-Newton method with rank 1 correction. So in each step, you estimate the inverse of the Hessian with this update rule, and you do a line search to find the best alpha. Is it clear what the algorithm does and what the motivation was? So we wanted to estimate the inverse of the Hessian. We use this update for that, and we hope it works. So some issues here is, so HK is symmetric, but it might not be positive definite. And that can be a problem, right? So in the Newton method, when we use Newton method, it was very important that the Hessian was positive definite. But if we use this estimation, it might be not. The other problem is that this expression here can be very close to 0, and then this update might blow up. Okay, so that's the issue with rank 1 update. It might be not, the estimated H might be not positive definite. So what can we do? We do a rank 2 update, and for that we will prove, or we could prove that if you use rank 2 update for H, then you can have this property that H will be symmetric and it will be positive definite as well, so the algorithm will be more stable. Okay, and the first of that kind of algorithm is the DFP, Davidson-Fletcher-Powell method. So it basically does the same thing that we just discussed, but instead of updating H with a rank 1 correction, it updates with a rank 2 correction. And sometimes this method is also called the variable metric method. Okay, so this is the pseudocode of the algorithm. H naught is an initial symmetric positive definite matrix. Gk is the gradient. You start from x naught. Step 1, you calculate the first direction. And the first direction is what you expect from the Newton method. It's the inverse of the Hessian multiplied by the gradient. Oops, I should be quick. Second step, you do a line search towards that direction. You update x to that direction. And then you update your estimated inverse of the Hessian with this rank 2 update that we have here. It's a bit ugly, but you can see that it's a rank 2 update, right? You add this rank 1 matrix and this rank 1 matrix. So it's a rank 2 update. And you might ask why this is the form of this update, but you can derive that how we derived the rank 1 update had the specific form. You can do some more complicated calculation for rank 2 matrices as well and prove that indeed this is a good update for this case as well. And there are important properties of this update. The first one is that this DFP method, if the H naught was positive definite, then in each update step, the estimation of the inverse of the Hessian will be positive definite as well. So it's better than the rank 1 update. And another important theorem is that you can prove that this DFP method is actually a conjugate gradient method, which might be surprising now, but it will have this property that these are the directions that we update. So Pi was, you remember the definition, is the difference between the x vectors between k plus 1 and k points. So you can see that they are conjugate directions, and it also has this consistency property that we wanted. And of course, that's trivial. Now, if Q is a quadratic function with the inverse of the Hessian Q, then after n step, you estimate correctly the inverse of the Hessian. And finally, the second method I want to talk about is the BFGS method. It uses a rank 2 correction. The difference between BFGS and DFP is the following. So this is how we updated H in the DFP method, right? However, you can notice now if you switch Q and P, they are kind of symmetric, then you could get an update for the Hessian, not just for the inverse of the Hessian, right? We just use these definitions to derive an update for H. But using these definitions, I could derive the same update for Q as well. Right? And now we would have an update rule for the Hessian matrix. And that's what BFGS does. So we have an update for the Hessian matrix. But in the Newton's method, we need the inverse of the Hessian. So what can we do? So here is the question for you. So you can see this update. We need the inverse. In each step, we update this matrix Q, and in an algorithm that uses this, for example, Newton's method, we would need the inverse of this matrix. So what can we do? If someone can answer, then you can leave. Yes, but so that just generally, here is a matrix. You can see this rank 2 update. I need its inverse. So for example, if it's just a rank 1 update, how would you calculate its inverse? You don't want to leave? You can use the Sherman-Morrison formula, if you remember. So that's the trick. So if you have a matrix A, you update with the UV transposed. You need its inverse. Then you can calculate its inverse as the inverse of matrix A plus some extra calculations. The problem that now we have a rank 2 update, so you just repeat this twice, this update here, and that's what BFGS does. So this is the algorithm. You update Q with, as you do in DFP, and then you do the Sherman-Morrison formula twice to get update for the inverse of the matrix. And if you do the calculation, you will get this expression here. Okay, and after this is the pseudocode. You do everything same as before, but for H we have this update. But other than that, it's exactly the same as the DFP method. And in practice, this algorithm seems to work better than DFP. So, and that's it for today. So we discussed modified Newton method, how to do rank 1 correction to estimate the inverse, and how to do rank 2 correction to estimate the inverse. And we discussed 2 methods that can do these updates. So if your homework is to implement BFGS or DFP, then now you should be good for that.